Welcome back. In this section, we'll be talking about some properties of functions, which include symmetries of functions, as well as average rates of change. So first off, to talk about symmetry, remember that we had already talked about symmetry of graphs of equations, that you could have something that's symmetric around the x-axis. You could have something that's symmetric about the y-axis. You could have something that's symmetric about the origin. And those were the sorts of things that we did previously. So if we're thinking about something that was symmetric about the origin, that would be something where if we had an x and y point, we would have the equivalent negative x, negative y point. When it was symmetric around the y-axis, if we had an x and y point, we'd have a point with the same y value, but with the opposite sign for the x value. And that when we were symmetric around the x-axis, we had whatever x and y point we might have, we would have a point with the same x coordinate, but with the opposite sign for the y coordinate. Now, when we're talking about functions, one of these symmetries would not be possible. You can see right away that the first kind that I have here, the symmetry about the x-axis, would not be possible. And the reason it wouldn't be would be if you were symmetric around the x-axis, then that means if you had the point xy, you would also have the point x negative y, which means you would fail the vertical line test. And so that means that that would be something that's not a function. So that's our answer for that. Why any function can't be symmetric around the x-axis. If you had something above and something below the x-axis as the mirror image, then you would be able to draw a vertical line that passes through that in more than one place. That means you would have something that's not the graph of a function. So that kind of symmetry we won't be seeing when we talk about functions. We'll only be seeing these two kinds, either symmetric about the y-axis, which as a function we call that an even function. And notice that the property here is that for an even function, that if you replace the x with negative x, you get the same y value. Or in other words, the y value for x and the y value for negative x are the same. That's our definition for what is an even function algebraically. It's a function where f of x and f of negative x are equal to each other. For the other kind of symmetry, symmetry about the origin, we call those odd functions, ones that are symmetric about the origin. Those are ones where, again, for every x and y point, if you switch the x coordinate to a negative, you'll get the opposite sign for the y value also. In other words, if you take the original function and switch the y value, that's the same thing as switching the x value in the original function. That if we swap x's with negative x's, then our y value should be the opposite as well. So the thing to notice here is that for all of this, if we're looking for identifying the symmetries of our function, we just really need to look at f of negative x. If it's the same as our original function, if we get the same y value when we swap the signs for x, then that means we're symmetric around the y-axis, we're even. Or if we switch x with negative x and we get the opposite sign for our y value, then that means we've got something that's odd. So for all of these, I'll be doing them all the same way. I'll be replacing x with negative x and asking myself, do I get my original function? Do I get negative 1 times my original function? Or do I get something different? If I get my original function, it's even. If I get negative 1 times my original function, it's odd. If I get something else, then it's neither. Then it's not even and it's not odd. That is one thing that I do want to clarify here. We're used to thinking about whole numbers as they're either even or they're odd. But for functions, you don't have to be even or odd. There's always the third possibility, which is you could be none of the above. You could be neither. Also, with functions, you can't be both. You cannot be even and odd at the same time. Because, for example, let's say that this was part of my graph. If you were even, you would have to have the mirror image on the y-axis, reflected in the y-axis. And if it was odd, you would also have to have this, which means that you would no longer be a function. So if you're even, you can't also be odd, and if you're odd, you can't also be even. But like I say before, it's possible that you might have none of those kinds of symmetries, so something like this is something that's not symmetric about the y-axis, and it's also not symmetric about the origin, it's not even, and it's also not odd. Alright, first one, f of x. Let's look at what happens when we replace x's with negative x. We'll have negative x to the 7 minus 3 times negative x cubed plus 1 over negative x, which, if you were to simplify this, negative x to the 7 is negative x to the 7. Minus 3 times negative x cubed. There we go. Had my cube inside the brackets. The cube should have been outside the brackets. Negative x cubed, rather, is negative x cubed. Multiplying that by negative 3 gives me positive 3x cubed. And 1 over negative x, that's negative 1 over x. And you can see that this is the same thing as if I were to factor negative 1 out of everybody. This is negative 1 times my original function. And so that means I can conclude that f of x must be odd. It's symmetric around the y-axis, symmetric about the origin. So this is what we need to do for these sorts of things, replacing our x's with negative x and asking, do we get the original function back? Do we get the opposite of our original function? Or do we get something else? So there we go. We've looked at f of x. Let's look at g of x now. And again, we're going to replace g of x. We're replacing the x with negative x. So that would be negative 3x in the numerator. Negative x when I cube it, it's negative x cubed. And this clearly is not the same thing as the original function. And it's also not the same thing as negative 1 times my function. You can see that this could be rewritten as 3x over x cubed minus 1 if I multiplied everybody top and bottom by negative 1. This is certainly not the same thing as g of x. And negative times g of x would be negative 3x over x cubed plus 1, which is not the same thing as what we have. So this means that this is not equal to g of x. And it's also not equal to negative of g of x. So therefore it's neither. It's not even, and it's also not odd. So if we were to look at the graph of this function, you'd find that it's not symmetric around the y-axis. It's also not symmetric about the origin. And now for the last one, I've got k of x, and I want to know if it's even or odd. So I will replace the x with negative x. And these, the x's are all being raised to even powers. Negative x to the 6 is just x to the 6. And negative x squared is just x squared. And you can see that, yes, this is our original function k of x back again. So when we replaced negative x, x with negative x, we got our original function back. And that means that k of x is an even function. It's symmetric around the y-axis. These are nice things to notice because if, let's say, we were graphing k of x and we knew that it was even, then I know that I only need to figure out what's going on the right side of the y-axis because what's on the left side would just be the mirror image. Or similarly, if I'm graphing f of x, once I figure out what's going on in quadrant 1, I know that the mirror image would be in quadrant 3. I would be able to figure out what's going on with my graph knowing that I've got that symmetry. Some other properties, and these are fairly natural as far as what they mean. The way that we're defining them might feel a little bit weird. So first off, we're talking about some open interval, open in the sense that I'm not including my endpoints. So an interval from A to B, not including the A, not including the B. And we've got some function that has a domain, has that as its domain. So to define what we mean by increasing, decreasing, or constant on that interval, when we say increasing, what we're saying is that if we've got that interval from A to B and we pick two x coordinates, one that's smaller than the other, x1 being smaller than x2, and if x1's y value is smaller than x2's y value, that means that this graph is heading upwards. This is an increasing graph. It's increasing on that interval. So if that's always the case, that whenever you pick any 2 points, the one on the left has the lower y value than the one on the right, you must be increasing. And the opposite would be if we're thinking about things that are decreasing. Those would be points where when you pick 2 points, the one on the left has the larger y value than the one on the right. That would be something that's decreasing. And if our points always have the same y value, so here when we pick 2 points, if the y values for those 2 points are always going to be the same, well then we must be constant, we must be horizontal. So as far as a graph goes, it's pretty obvious then when things are increasing, decreasing, or constant. Increasing is when the graph is going up, decreasing is when it's going down, and constant is when the graph is horizontal. The next part is talking about extrema, talking about maximum and minimum values. There's two different kinds of extrema. There are local or relative is one way of calling them, and the other kind is absolute. So here again, we're thinking about an interval of real numbers. And if you've got something that's a local maximum or a relative maximum, then that would be a point where the y value is larger than all the other y values in that interval. So if you're thinking about a function that wiggles along like this, and if we're thinking about this as being our interval from A to B, you would call this point a local maximum because its y value is the largest of all of these points in that little interval. And similarly, you could say things about local minima or a relative minimum. That would be something where on our interval, it happens to have the smallest y value of all the y values in that interval. So a local extremum, that's any local minimum or local maximum. These two words mean the same thing, local and relative. They both are referring to largest values within their little interval or smallest value within their little interval. So if we're looking at this graph, and if you're interested in where is it increasing, where is it decreasing, mins and maxes and all the rest, you can say, number one, that where is it increasing? Well, we're increasing until we get up to 1, negative, and then we increase from 1 afterwards. So where are we increasing? We're increasing all the way until we get to -1, and then we increase after 1. One thing to note here is that I'm not including the -1 or the 1, partly because of the definition that I gave. When we said for increasing or decreasing, we were thinking about an open interval, one that's not including our endpoints. But the bigger reason as to why I'm not including them would be, at this point, you're not really increasing anymore. You increased until you got there, and you'll be decreasing afterwards. But at that point, you're really neither increasing nor decreasing. You're changing direction. So that's why I wouldn't include the -1, and for a similar reason, why I didn't include the +1. So we're increasing up till -1 and after 1. Where are we decreasing? Well, just in that little interval there between -1 and 1. Again, not including those endpoints. Where do we have a local maximum? Local maximum happens when x equals to -1. What is the local maximum value? That would be the y value of 4. So this is something to keep in mind when we're talking about maximum values and minimum values. There's the question of where does it happen or when does it happen? That's asking what x value is the value for the minimum or maximum. The question of what is the minimum or maximum value, that's asking for the y value. So for C, where is the local maximum? It happens when x is equal to -1. What is that local maximum value? It's 4. Local minimum, where does that happen? It happens when x is equal to 0. When x is equal to 1. And what is that minimum value? The minimum value is 0. The one thing that you might be noticing here is that even though we're talking about a maximum value of 4, let's say, that's not the biggest y value of all. In fact, for this graph, there's no biggest y value because we keep going up forever. And 0 is the smallest y value in its little neighborhood, but it's not the smallest y value of all. We've got smaller ones over here, and in fact, there's no smallest because we'll keep going down forever. But there are going to be some graphs where maybe we do have a largest value or a smallest value. And to talk about those, we call those absolute extrema. The absolute maximum, that's the largest y value of all the y values. So for every x in the domain, that value is the largest. Well, then that's the absolute maximum. If you have a y value that's smaller than all of the other y values for all the x's in the domain, that's the absolute minimum. So for this graph, we've got a couple of points that are on it. One thing just to note here and just to zoom in, that this graph has arrows on the far left and far right, which means that this graph will continue going up in this direction forever and continue going up in that direction forever. And that's important here because if we're thinking about talking, let's say, about the maximum values first, we can see that we do have a local max. So a local maximum happens when x is equal to 3, and that maximum value is 4. But if you say, is there an absolute maximum value? Is there a largest y value? Then the answer is no. And that's because the graph keeps going up forever. So that means there should be no largest y value. So we do have a local max that happens when x is equal to 3. But that means we also can say that there's no absolute maximum. Now, on the other hand, for minimum values, you can see that we do have two local minima. So for the minima, so we have one local minimum happening at x being 1, and for that the value is -2, and also at x being 5, and for that one the value is +2. But if you're asking me the question of what is the absolute minimum, that would be what is the smallest y value of all, and the absolute minimum value is -2. So I could say here for the absolute minimum, the absolute minimum happens when x is equal to 1, and that minimum value is -2. So here we do have a smallest y value, and the smallest y value for this function, -2, and that happens when x is 1. So that means you can have a point like this one, 1, -2, that it's both a local minimum, it's the smallest y value in its neighborhood, and it's also the absolute minimum. It's also the smallest y value of all the y values. All right. One other thing just to talk about briefly here would be average rate of change. Average rate of change is just measuring how much does the y value increase or decrease over some interval of x values. And I've got a little motivating example here. F of x telling you the population of a town on the first day of year x. So f of 2000, that would be the population of the town in the year 2000. F of 2010, that's the population in the year 2010. You can find out that for this story that I have here, we begin with 550 people, and then 10 years later, there's 750 people. So we've increased by 200 people over 10 years, which is an average rate of change of 20 people per year. So that's not to say that the town is every year getting exactly 20 people more. So the year 2001, we didn't necessarily have 570 people in town. It's that if you look at the average of where we started at and where we ended at, we've increased by 200 people over 10 years. So the average is an increase of 20 people per year. Now, nice thing here is this is really just the slope of the line connecting those 2 points. The point from the beginning of that interval, when x is 2000 and the population is 550, and the end of it, when x is 2010 and the y value is 750. And in fact, if you calculated the slope of those 2 points, you would find that the slope is 200 over 10, which is the same thing as 20, telling you that you're increasing by 20 people per year. If the average rate of change was negative, then that would be telling you that the population would be decreasing for this town, that it would have gone down by a certain amount per year. So, since the average rate of change really just is a slope, then that's all it is. If you want the average rate of change of some function over some interval from a to b, then you'll have the point a f of a, you'll have the point b f of b, and you're just going to calculate the slope of those points. So the change in the y values divided by the change in the x values. F of b minus f of a over b minus a. And a nice little thing here is that this is a connection to the difference quotient. If you're looking at this drawing and thinking back to 3.1, this is actually similar to the difference quotient that we saw back there, that when we were measuring the difference quotient, that was, again, the slope of the line that passes through those 2 points. That kind of a line that cuts through a graph in 2 places, you call that a secant line. So here, the line that's in red, this would be the secant line that I would have that cuts through the 2 points on my little parabola. Secant coming from the Latin secare, meaning to slice or to cut. So the secant line cuts through that function in 2 places. It sounds more complicated than it is, but really all a secant line is just a straight line. And we know what the slope of that straight line would be. The slope of that straight line is the average rate of change. Because remember, the average rate of change is just the slope of the point going from when x is a to when x is b. So if somebody were interested in finding the secant line for a function, what they'd be interested in is finding the line that goes through from some beginning point to some end point, and the slope of that line, that would be the same as the average rate of change for our function. So if we're interested in this function, what is the average rate of change over the interval from 1 to 3, I would first need to find out, well, what is f of 1? And I could find that that is 0. And I find f of 3 rather, is 2. So we have 2 points. We have the point 1, 0, and we have the point 3, 2. And so for our average rate of change, that's just the change in the y values over the change in the x values. So change in the y values, 2 minus 0, over change in the x values, 3 minus 1. And then just simplifying, that's 2 over 2, which is the same as 1. So that means that if we were to graph f of x, and whatever it happens to look like, and we haven't talked about how we would graph this function or how we would be able to tell what it looks like, but if we were to graph it, and if we were to draw f of x, we'd find that it has 1 point, 1, 0, and another point, 3, 2, and that if we connected those 2 points with a straight line, the slope of that straight line would be 1. And that straight line, that's exactly what we want to create in part B, the equation of that straight line. And we have everything we need because we know there's these 2 points that are on the line, 1, 0, and 3, 2. And we know what the slope of the line is. This line has a slope of 1. So I'm just going to use my slope point form. Y minus the y coordinate equals slope times x minus the x coordinate. And I'll use that first point 1, 0. So putting in 0 for y, putting in 1 for x, and putting in my slope of 1 that I just found, because the slope of my secant line, that is my average rate of change. And then just simplifying. There I go, the equation of my straight line that passes through my parabola there when x is 1 and when x is 3 happens to be the straight line y equals x minus 1. Now, as I said before, this slope of a secant line is the same thing as the difference quotient. Rather than defining it as going from point A to point B when we talked about average rate of change, then for a difference quotient, we said, well, we'll start at point X and go h units over, which means we'll go from x to x plus h. But it's still measuring the same thing. If you were to think about these 2 points, x, f of x, x plus h, f of x plus h, those would be these 2 points that happen to be on the curve, and that the line that connects them, the slope would be the change in the y values over the change in the x values, which exactly is the difference quotient. So the average rate of change, that's really the numerical version of the difference quotient. When we find the difference quotient, we're leaving things in terms of x's and h's. When we find an average rate of change, we're actually evaluating with numbers, but both of them are really talking about the same thing. How is the graph changing over that interval from x to x plus h, or from A to B?